and he will talk to us about computing numerical solutions of the modified Buckley-Leverett equation with
then it's going on.
Capillary pressure.
So thank you. It's a great honor to be here in the occasion of Dan's birthday. My stay here at IMPA was about 4 years, for 1 year as a postdoc and more 3 years as a visiting research position here under the direction of Professor Dan Marchesin. And actually, before that, during my PhD, Dan's for sure established a bridge between IMPA and Instituto Politécnico Nova Friburgo, and I thank you, Dan, for his contribution in my career, for sure, definitely. So in this talk is my way to give thanks to Dan, and I try to do some effort to establish some connection of many of the Dan's work with this subject, from numerics, from theory and applications. So this is the plan of the talk, and the idea is to design a numerical scheme for numerical solution of Buckley-Leverett type equations with a dynamic effect in the capillary pressure. In the literature, people call this as a pseudo-parabolic Buckley-Leverett model. So, among all proposed theories about this subject, the one that has the attention of the community is the one that introduced by Johannes and Gray. And there are many results from theory, applications, and numerics, as we can see here. And in this work here is a very nice survey about the subject that range from theory, numerics, and applications, including laboratory experiments. So this is the situation, the capillary pressure. The traditional is only this black part here, and the new one is this red one. And the tau is a dynamic effect that measure, if understood quite well, the disorder of the medium. And phi is the rock porosity, and D is the static capillary pressure, as usual. In this work, this is a constant. And we can see here from the literature, doing some kind of research about in the past, we can find some situations in the very past, like this Muren work here, and the Rubinstein here, about these effects in porous media from laboratory experiments and also from theory and applications. This is very nice work too that accounts this kind of effects as relaxation. And here I will follow precisely exactly this model introduced by Van Doyen, Petelier, Pop at Cyan in 2007. So in this paper here, there is no gravity. This is important. No gravity here. But after studying a little bit about this, the effects of the balance between the diffusive effects and the first order hyperbolic equations give rise to the question how to measure the balance between these two effects. And when gravity enters in the picture, these seem to be more complicated, as we'll see later, taken from other works. And in these works here, we have the possibility of model the dynamic capillary effects, at least in my opinion, since we have precisely this kind of behavior of the balance between the gravity, the convection, and the diffusive effects in the porous medium. And then these two works here that I took for motivation from the Norwegian Sleipner gas field, they used immiscible three-phase and wag floating. So three-phase system. And from Petrobras here in Brazil, we have some kind of wag experience in deep reservoirs in the pre-salt. So put this together, we can see this sample from Petrobras. It's not a real one, but that resemble what happens in practice. This is from Petrobras, actually. And we can see here that we have huge reservoirs, something like 16 kilometers, and from Y and X directions, and depth is something like 500, 600 meters, many layers. And as we can see here, we have the interplay between the gravity and the diffusion. So this mechanism appears naturally in the model. So in this situation, as described in the literature, the dynamic capillary pressure can be used to account some kind of laboratory experiment that observes such kind of behavior. So here's the point, the key point actually. Dan Marchesin contribution on three-phase flow, many works, and in my modest opinion, this should be the basis to understand the features, the mathematical features about this three-phase flow system, about this kind of model, and in the next step, to account the capillary pressure, the dynamic capillary pressure. So this is the model. In blue is the Buckley-Leverett one, and in red is the new term, along with initial and boundary condition. And to go into the point, let me show some quick view, the behavior of the monotone, the qualitative monotone, non-monotone behavior of this kind of solution. And as I mentioned, we can find some works, experimental works that observe this kind of overshoot of the saturation. So the first case, this is important, linear diffusion, like this. The Buckley-Leverett type shock, the Buckley-Leverett flux function. 2 here is the ratio between the ratio viscosities. This is the initial data. So we have a shock here and a constant state and a shock behind it that resemble a rarefaction. This is in accordance with the exact solution as shown in the work of Petelier with rigorous analysis. The second one, the same model, but the only difference is the states. The Riemann data here. You see? So we have this behavior, something like a damp oscillation behavior in the solution. And the second test with nonlinear diffusion, we have, this is the formulas that they used in the paper. And here's the solution. So somewhat kind of combination of this behavior, decaying, oscillation, and with this overshoot on the saturation. So more about Dan's contributions. If you write this as in relaxation form, for instance, if formally we multiply this equation for this parameter and take this to 0, you can see the equilibrium here. So this structure can be used to understand in a more rigorous way. In the works of Petelier, they did not use this kind of formalism of relaxation, and I think that we can use this to understand this, the role of this parameter here. That work they found to be a bifurcation parameter here. In this case of relaxation, this could be some kind of equilibrium state. So our understanding was motivated by some of Dan's works that model in the past, recent past, hysteresis on three-phase flow via relaxation. So this motivates us to understand this viewpoint, and not only about this, but also try to develop some kind of projection method to solve more complex systems. But the basic is the work of Dan, for sure. And some remarks, as I mentioned before, the new thing here is in the work of Van Doyen and Petelier-Pop, they do not cite explicitly this work, and this is because the specific behavior of the equation. And this actually put everything together is our starting point to construct the numerical scheme. No use of splitting, although we use this in the preliminary part of the research. So, classical polynomial split may fail. We were to identify two concrete examples. In this first one, the were in the first order hyperbolic part, and the discontinuous capillary is the trigger to make fail the splitting. We solved this partially, at least for some models. And in this case here, we're also able to give you another example in which the splitting fails. But in this case, we're able to fix. It's possible to reconstruct the splitting and get the right solution. Just to give an idea, as classical one, by splitting advective and diffusive process. As I mentioned before, in black is the correct solution. On the left, the frame, and here is our solution. That's wrong. You can refine the mesh. It's not possible to get the correct solution. On the right, the black, the correct solution, and here the wrong solution. You can refine the mesh, no way. But if we do some kind of splitting by balancing the dispersive behavior in both terms sequentially, then you can capture the expected solution. So this is the computed solution as we refine the mesh, going to the right profile, on the left, on the right. But in this work, so after this, we were able to be more motivated to design a numerical scheme without any kind of intrusive splitting. So to do this, we revisit this work of Dan Marchesin by using splitting to understand the behavior, in which we used the mixed and finite element approach combined with the finite element approach. So this is the idea. The same model, but now we rewrite the equations in the spirit of the mixed formulation. So this is the equation 9 to the Darcy velocity, like this here, and the pressure, and this equation here to the saturation. So we now have this coupled set of equations that must be solved sequentially. So the idea is to use standard finite volume here, L1 separation theory, and here we use the mixed finite elements. So this is the next slide will be the discretization of only of these equations here. So the idea is by using the Harvey atomized space, we take linear to the velocity and piecewise constant to the pressure. This is very interesting because after the standard calculation, we found this discrete system. In black is the mixed and finite element formulation to the velocity and to the pressure, and in red is the solution to the finite volume, plus this equation here, that must be solved by any finite volume standard approach. The key idea here is to solve this sequentially. That, in my opinion, is the best we can do here, by using finite volume numerical fluxes to the first order hyperbolic parts, and by using mixed finite elements to the other terms. What is important here, how to construct these numerical fluxes here. So that's the point that we link to the work of Benjamin Bonamahony, that has this kind of type equation with this perceived here. As I mentioned, in the work of Petelier and the other ones, does not appear explicitly this kind of citation of this work, but to us there is a close connection between them, and this allows us to choose this Rich-Meyer numerical flux that accounts to the dispersive effects and to the diffusive effects. We also use the classical Nessiahu-Tadmor numerical flux that is quite diffusive here, and the solution is not so good as by this simple choice. The influence of the parameter tau, just as a verification of our work, this is precisely as appear in the work of Petelier. As we decrease the value of tau, or as we increase, we can see more damped oscillation. This is precisely what appears there. This is our numerical solution. This is again our numerical solution, and precisely what appears in this work here. The same velocity, the same states, the same the same structure of solution. And now we give us another step to the two-dimensional problems. The same formulation, but now in 2D. Here we use, in the spirit of IMPA's approach, as I said before, we solve pressure velocity problem and the parabolic transport equation sequentially. In that formulation to the transport equation, as we treat the first order term and somehow as a source term, the mixed finite element approximation leads us to a saddle point problem, and with the introduction of the Lagrange multiplier, we can have in the end, after some kind of linearization, a positive definite matrix. So we can use the same linear solver to the numerical solution of the pressure velocity problem and to the transport equation. So this is the same structure of the fractional flow functions and the same nonlinear diffusive effects here, as I mentioned before, the same capillary pressure. This is a very simple example. So we have high permeability values here, and a slow value here. Is the velocity field, and you see the velocity field that is going to the regions that we expect to this behavior, and this is the saturation in the front, and here is the good view to see if we have no exclusion oscillation, and you see here the behavior that appears in this region that I mentioned before, with the value of the permeability less than what appears here. This is like a slide problem. We have no flow on the boundaries, an injection here, and we capture nicely the structure. We also have some kind of solutions in a heterogeneous medium, but for the purpose of this talk, I think this gives us some good confidence that we are doing the right thing. So we use this kind of approach for Capizzi equations, for nonlinear transport equations with non-local fluxes and initial data as a measure with viscosity greater than 0, and also with viscosity equals 0. Those are open problems, how to get existence and so on. How in this case here, we can have a blow up, for instance, of concentration type, but we use these ideas to have some insight in developing some new numerical schemes to handle these problems. So, as a perspective, numerical analysis, if it's possible, and some kind of relaxation system by using this idea. So, the key point is the thank you, Dan, for your contribution. Development of industrial and applied in Brazil, for sure. I'd like to share with my colleagues the contribution of Dan in these 2 prizes. The first one is Petrobras IMPQ Prize for Innovation, and the second one for the Brazilian Society of Computation in Applied Mathematics. Those are related to my PhD thesis, but as I mentioned in the beginning, Dan was the key player, for sure. Of course, many PhD, postdocs, and I think the legacy of Dan is quite clear, scientific descendant. He did his job, for sure. And special thanks to Dan, and I thank you, Dan, with your support in your own way. Maybe after some years, now I can understand how the way you think, and I try to learn more. And I thank you, Dan, for your continued support. I'll stop here.
Comment. I didn't do any of it. He needed the culprit, so.
I have just a side question about the Liu Jinshin. Which is that, Hailiang Liu or Taiping Liu? What is the reference to the Liu?
Taiping Liu.
Taiping Liu.
Yes.
Or just general relaxation.
Yes.
Okay. Thank Eduardo again.